All right, let's compute these acceleration level kinematic equations in vector form and put them in the coordinates, and the zeroth coordinates. Okay, so let's start with this first set of equations. Acceleration of point B in 1. What is that? So the velocity of point B in 1 was d4 dot in the y1 direction, if you recall. Acceleration of point B in 1 is therefore going to be d4 double dot in the y1 direction. Okay? Plus 2 times angular velocity of 1 in 0. What is that? That is theta 1 dot in the z1 direction, cross velocity of B in 1, we said was d4 dot in the y1 direction, plus angular acceleration of 1 in 0, that is equal to theta 1 double dot in the z1 direction, cross p04, that was d4 in the y1 direction. Correct? Carry on. I'm going to carry on writing. Angular velocity of 1 in 0 is going to be theta 1 dot in the z1 direction, cross theta 1 dot in the z1 direction, cross d4 in the y1 direction. Okay. Over here we are at this term right there. Angular velocity of 2 in 0 is going to be theta 2 double dot in the z2 direction, cross p42. What was p42? p42 was, if I recall, negative a2 in the y2 direction. Let's recall that. p42 is the vector that goes from the origin of the fourth frame to the origin of the second frame, right? And that vector is in the negative y2 direction. And the amount we have to go is equal to a2. So indeed, it's going to be negative a2. This one here is going to be, oopsie, negative a2 in the y2 direction. Yep. And then plus angular velocity of 2 in 0 is theta 2 dot in the z2 direction, cross angular velocity of 2 in 0, theta 2 dot z2, cross p42, which we said was equal to negative a2 y2 equals 0. Okay, let's keep on working at this, on this. d4 double dot y1 plus, so I'm going to do this cross product. I need to do the cross product of z1 and y1, which gives me negative x1, if you recall. So this is going to be negative 2 times d4 dot theta 1 dot in the x1 direction, plus this cross product right there, that's going to be z1 cross y1 again, which means that I need a negative rather than plus. Negative d4 theta 1 double dot in the x1 direction over on this term, plus, so first I have to do this cross product, as you can see. I have already done that with d4 replaced by d4 dot over here. So that's going to be, what is that going to be? That's going to be plus theta 1 dot z1 cross minus d4 theta 1 dot in the x1 direction, right? Okay, so I have a z2 cross y2 here, but with a negative sign. So that's negative x2 with a negative sign, which means x2. So this I have here plus a2 theta 2 double dot x2 plus theta 2 dot z2 cross, again here I have z2 cross y2, which is minus x2 with a minus sign. It's equal to x2. So this is going to be equal to a2 theta 2 dot in the x2 direction equals 0. Okay, one more step. This is going to be, I can't simplify this term, so I'm writing it as it is. Neither can I simplify this term, writing it as it is. Cannot simplify that term. Okay, I can simplify this next one. This says take all the scalars out and do the cross product between z1 and negative x1, which gives me a negative y1, right? Because z1 cross x1 is y1. With a negative sign, I have a negative. So I have a negative here. It's going to be d4 theta 1 dot squared in the y1 direction. Great. Okay. Over here, plus 8, sorry, plus, oh my, again the fat fingers, a2 theta 2 dot x2, and then I have a z2 cross y, x2 term, which is a plus y2, so this is going to be plus a2 theta 2 dot squared y2 equals 0. And finally, I can write them in the zeroth frame, right? Now, what I have is d4 double dot. If I look at the components of y1 in the x0, y0, z0 directions, they are negative sine 1, cosine 1, and 0. When I say sine 1, that means sine theta 1. Cosine 1 means cosine theta 1, of course. Okay, so minus 2 times d4 dot theta 1 dot x1 in the zeroth frame looks like cosine of theta 1, sine of theta 1, and 0, minus d4 theta 1 double dot, again x1, cosine 1, sine 1, 0, minus d4 theta 1 dot squared, and y1, which is negative s1, c1, 0, minus a2 theta 2 dot x2, which is cosine 2, sine 2, and 0 in the zeroth frame, plus a2 theta 2 dot squared. Sorry, this one, I'm missing a double dot here. Sorry about that. And hence I'm missing a double dot there. Okay. Okay, everything is in order now, hopefully. a2 theta 2 dot squared times y2. And y2 is minus sine theta 2, cosine theta 2, and 0 in the zeroth frame. And this here is the final equations that we would code in MATLAB or Julia to be able to solve for our acceleration variables. Of course, by itself, it won't suffice. We need a second set of equations, which will come from our second acceleration level equations in vector form, which is this guy right there. Okay? Let's go back and do that. So just for looking at it as I'm writing it, I'm going to copy it again and I'm going to delete it later. So let's copy that. Copy. Okay, let me paste it over here, and I'm going to start with, then I'm going to start working on the next page. Okay. So the acceleration of 1 in 0 is given by theta 1 double dot in the z1 direction cross p03. P03 was, I believe, a1 in the y1 direction plus angular velocity of 1 in 0 is theta 1 dot in z1 direction cross theta 1 dot in the z1 direction cross a1 y1 plus acceleration of 3 in 0 is theta 3 dot and another dot, theta 3 double dot in the z3 direction, cross p35. Let's recall what p35 was. That is equal to negative a3 in the x3 direction. Plus, oh, whoa. Sorry, I definitely need a parenthesis here that I missed. Now I realize it because when I copied it over here, I saw it. This needs a parenthesis right here. Okay, back to our simplification of the second acceleration level equation. Angular velocity of 3 in 0 is theta 3 dot in the z3 direction, cross theta 3 dot in the z3 direction, cross P35 again over here, so that's going to be negative A3x3 minus acceleration of d in 0. Now that is going to be negative d5 double dot in the x0 direction. Why? Why? So to understand this, let's go back to our velocity level analysis, right? Where we talked about, let's go back here, all the way here. This one right there, this term right there was equal to negative of the velocity of the point D in the 0th frame. That's the negative of velocity of D in 0. Acceleration of D in 0 is the derivative of this term right there, right? Since this is the negative of velocity of D in 0, the acceleration of D in 0 is essentially going to be the derivative of that guy right there in 0th frame, which is d5 double dot x naught plus d5 dot ddt in 0 of x naught. Now ddt of 0 in 0 of x naught is 0. So we're left with d5 double dot in the x naught direction for the negative of the acceleration of d in 0. Okay? So go all the way back down there. So essentially, the negative of the acceleration of d in 0 must be d5 double dot x naught. So hence, we have this term right there that corresponds to that. Okay? Okay. So we carry on our computation. Over here we have simplified further. So let me just get rid of that actually. Okay, so z1 cross y1 is minus x1. So this is going to be, now I can put this a1 theta 1 double dot x1 with a negative sign, of course, that I'm missing. So plus angular velocity of theta 1 z1, theta 1 dot z1 cross z1 cross y1 is again negative, so this is minus a1 theta 1 dot in the x1 direction, plus z3 cross x3 is plus y3, but with a negative sign here means that I need a negative sign there. So this is a3 times theta 3 double dot in the y3 direction, plus theta 3 plus theta 3 dot in the z3 direction cross z3 cross x3 is y3. I have a negative sign, so negative a3 theta 3 dot in the y3 direction, plus d5 double dot in the x0 direction equals 0. Simplify it further, I have minus a1 theta 1 double dot x1 minus a1 theta 1 dot squared. Now I need a z1 cross x1 term, which is y1, minus a3 theta 3 double dot y3, and another minus a3 theta 3 dot squared x3, but z1 cross y3 is negative x3, so I need negative and negative makes a positive right there. Okay, and then plus d5 double dot in the x0 direction equals 0. And finally, I can move these in the 0th frame, write it in the common frame, and I choose to write it in the 0th frame. This is going to be minus a1 theta 1 double dot x1 direction has components cosine 1, sine 1, and 0 in the 0th frame, minus a1 theta 1 dot squared y1 direction has components minus sine theta 1, cosine theta 1, and 0 in the zeroth frame, minus a3 theta 3 double dot. y3 direction has components minus sine theta 3, cosine theta 3, and 0 in the zeroth frame, plus a3 theta 3 dot squared. x3 direction has components cosine 3, sine 3, and 0, plus, of course, d5 double dot 0, 0 equals 0. And finally, I have my acceleration level equations. This one right here and that one right there. Okay, so let me pull them together and pull them together and designate them formally as the acceleration level equations in the zeroth frame. This one right there. So let me put a separator here, and that one right here. Oops, I didn't want to do that. I wanted to copy and paste. Very good. The final step, of course, as you can see, first of all, as you keep differentiating, the equations get more and more involved. However, it's hard to write them. It's long to write them. It's not hard, but it is long, tedious to write them. But the equations are actually not difficult, because if you look at these equations, let me label them as AL1 for these guys, and for this one AL2. If you look at AL1 and AL2, acceleration level loop equations, what you observe is that like the velocity level equations, these acceleration level equations are actually linear in the unknowns. What are the unknowns? The unknowns are, we know theta 2 double dot, but we don't know theta 1 double dot. We don't know theta 3 double dot right there. Yeah. d4 double dot and d5 double dot. We don't know them. So these are our unknowns, and you can see that they enter these equations in a linear fashion. So when we want to solve these equations, we can again set up an equation of the form ax equals b and just solve that linear system of equations. So next order of business is to set them up. Okay, so I'm gonna set up an equation called, just like I did for the velocity level equations, that looks like ax equals b, where x contains my unknowns, which are what? Theta 1 double dot, theta 3 double dot, d4 double dot, and d5 double dot. Put a transpose here, so it's a 4x1 vector. B is going to contain all of the knowns, and of which we have quite a bit of them, quite a lot of them. So for example, for the acceleration level equation AL1, this is completely known. This is completely known. That is completely known, right? That guy here is completely known. So all of them are going to go and form a part of B. For the AL2, this part is completely known. This part is completely known. Moreover, in AL1, this part is also completely known because we are driving the second link. Hence, we know what theta 2 double dot is. Okay? So all of them, all of these all of these terms that are underlined with red are going to go into the B vector. Okay? So let us construct the B vector first. So B vector is going to consist of the first two rows are going to come from AL1, and the second set of two rows they're going to come from AL2. Okay, so whatever comes from AL1 looks like 2 times d4 dot theta 1 dot cosine 1 minus sine 1 d4 theta 1 dot squared plus a2 cosine 2 theta 2 double dot and plus a2 sine 2 theta 2 dot squared. That's the first element of B. Second element of B looks like 2 d4 dot theta 1 dot sine 1 plus cosine 1 d4 theta 1 dot squared plus a2 sine 2 theta 2 double dot and then a minus a2 cosine 2 theta 2 dot squared. The third element of B is going to come from our first row of AL2, and that is going to look like minus a1 sine 1 theta 1 dot squared minus a3 cosine 3 theta 3 dot squared, and that's it. And the final element of the vector B comes from the second row of our AL2 equations, and that is going to look like a1 cosine 1 theta 1 dot squared and a minus a3 sine 3 theta 3 dot squared. Very good. We have our x and b vectors. What is our A? A is going to be again a 4x4 matrix. Indeed, this A is going to be the same A as we had in the velocity level equations. But let's look at it anyway. So the first row is going to come from the first element in the first row is going to be the coefficient of theta 1 double dot, which we see here as minus d4 cosine 1 minus d4 cosine 1. The second element of the first row is going to be the coefficient of theta 3 double dot, and we see no theta 3 double dot in AL1, the first row of AL1, so this is going to be a 0. The third element in the first row is going to be the coefficient of d4 double dot, that is negative sine 1. The final element in the fourth element in the first row of matrix A is going to be the coefficient of d5 double dot in AL1, the first row of AL1, which is again 0. Okay, let's look at the second row of AL1 now and look at the coefficient of theta 1 double dot. That reads minus d4 s1. Again, I'm looking at the second row of AL1, looking for the coefficient of theta 3 double dot. I see none, so it is a 0. The coefficient of d4 double dot in that same equation is cosine 1, and the coefficient of d5 double dot is 0. That's the first two rows of matrix A. Second two rows of matrix A are going to come from the first two rows of AL2. So look at that. The coefficient of theta 1 double dot in AL2, in the first row of AL2, is minus a1 c1. The coefficient of theta 3 double dot in first row of AL2 is equal to a3 s3. The coefficient of d4 double dot in the first row of AL2 is 0. The coefficient of d5 double dot in the first row of AL2 is 1. The coefficient of, again back to here, the coefficient of theta 1 double dot in the second row of AL2 is going to be minus a1 s1. Coefficient of theta 3 double dot in the second row of AL2 is minus a3 cosine theta 3. Coefficient of d4 double dot in the second row of AL2 is 0. And the coefficient of d5 double dot in the second row of AL2 is also 0. So we have our linear system of equations, ax equals b. Now all we need is to plug in numbers and let MATLAB or Julia solve it. So if you look at this matrix here and compare it with this matrix right there, you see that they are exactly the same matrices. Okay. And I solved them. I plugged them in MATLAB, or in actual Julia, and the solution turns out to be the following. Theta 1 double dot comes out to be equal to minus 225,205.789 radians per second squared. Theta 3 double dot is going to be equal to, turns out to be equal to 268,839.49747 radians per second squared. The 4 double dot comes out to be 1.23 times 10 to the 7 millimeters per second squared, and D5 double dot turns out to be minus 4.9.6068 times 10 to the 7 millimeter per second squared. So that's the end of the kinematic analysis for this mechanism. And hopefully in the next video I'm going to go up to the computer, actual computer, and show you how I coded these up and got these numbers. All right.